Okay, so section 4.3 is titled Arithmetic in the Hindu-Arabic Numeration System. You need to know that Hindu-Arabic is your numeration system. Maybe you didn't know if that's what it's called. Every now and then there's weird things that go around on social media and they make it sound like, like, can you believe they're teaching the Hindu-Arabic numeration system in schools? Well, I sure hope so, right? Because somebody doesn't know that that's what they use all the time. But that's what it is. We're using the Hindu-Arabic numeration system. There are several things that you know, but you probably haven't thought of in this way before. So for one, expanded form is the form in which the values of the digits in each position are made clear. For example, if we have the number 942, that's not how you normally say it, right? Like you say it with its place value attached. We say 942. It is understood to be 9 hundreds, not just 9, 4 tens, right, 40, and then 2 ones. And you can kind of think about the expanded numeration kind of like our bills. It doesn't work once you get past $100 bills because we don't have $1,000 bills, but as long as we're reading the hundreds, it's okay. If you only had hundreds and tens and ones, this is what it would look like. Now we have some other bills, I get that. But if you restrict your perspective to that, that's what we say when we look at our numeration systems. So what we're going to do is we're going to take a look at how we understand that in numerically written form. And I'll do that with this one first. For example, this says 900, so we think about this as 9 times the number 100 plus 4 tens, so this is 4 tens, and 2 ones, right? So you're writing it next to the amount that it's being multiplied by its place value. Now, it's important to also understand, because my math lab does this, not necessarily because I like that it does this, right, is that we can take each of those powers of 10, or each of those like 10, 100, 1,000, those bases that we're multiplying by, the number next to it, and we can express them as a power of 10. Okay, we have a base 10 numeration system. It was probably in the video that I posted. It's because you have 10 fingers, and like that's legitimately why. Okay, because you have 10 counting fingers. That's why we have our base 10 numeration system. So if we were like Fred Flintstone, did I say this in my video? Excellent. We would be in a base 8 numeration system, right? They only have 8 fingers when you look at most cartoon characters, right? Yeah, and it looks like that, like RJ just said. So it's your thumb and your 3 fingers. That's what it looks like. All right, so they write this with powers of 10. I like this better, but I don't get to choose some of the things that are the programming inside of my math lab. So it's going to look like this. Instead of having the number 100, they're going to write it as a power of 10. So it's 10, and it's 10 squared, because that's what 100 is. And instead of just writing 10 down over here for the 4 times 10, they would write it as 10 to the 1. And then does anybody know what the power is to get you a number of 1? Say it louder, Polly.
0.
It's 0. So this is 10 to the 0. One of the ways that you can remember the powers is simply by looking at how many zeros are present, right? In the number 100, there's 2 zeros, so it's a power 2. Okay? So if you had the number 10,000, so pause with me for a moment to consider this. How many zeros are there? 4, so this is 10 to the 4th. Okay, so you can always know the power of 10 that you're working with because it's the number of zeros. And that works with the number 1 as well at the end, right? The number 1 is the power of 10 to the 0 power because there are no zeros. There's 0 zeros, right? All right, so we're going to do this with a couple of with one example, and then we're going to do it backwards with the other one. So we're going to take a number. This number is 12,398, and we're going to write it in expanded form. Okay, so I'm going to write it in 2 steps. I think my math lab has you write it in 2 steps. At the very least, it's going to have the second step listed, but we'll take it steps at a time. So we've got the number 1. How many ones does this represent? It's not really the number 1. What number is this 1's place value? It's the 10,000s. How about the number 2? It's the 1,000s place, right? The number 3. That's the hundreds place. The number 9, that's our tens place. And the number 8 is the ones place. Okay? And then if we're wanting to write that in sort of a condensed version with the powers, which they like for you to see, written that way at the end, what's the power of this 10? 4. It's the one that I mentioned in the previous screen, right? That's not a very good 4. Let's try that again. That's better? How about the number 1,000? 3. The number 100? 2. The number 10? 1. And the number 1 is 0. Now, you might ask yourself, does it always just go down in power? And it does, as long as you don't skip any. So let me just bring your attention to one other caveat with a very simple one I'll do. I'll just do the number 102. So let's say you had 102, so there's a 0 placeholder there. You see that 0? There's a couple of options. One option is that you can express it with the 0. So there's 1 100, there's 0 tens, and there's 2 ones. Or option number 2 is that you could leave the 0 out if MyMathLab permits, and it might be written like that. So if you choose to do the second one right here, you need to understand that your powers are not just going to decrease. You're skipping one entirely. So just be careful. My preference when I do them is to leave the 0 in. It doesn't bother me at all to have the 0 placeholder there because then I can look at the powers they saw go downhill. Okay? Good? Okay, we're going to go in reverse order. Right here is our expanded form, and we're going to write it back in our standard. We call it standard form for our number. So we have 5 times 10 to the 5th, 0 times 10 to the 4th, 3 times 10 cubed, 5 times 10 squared, 6 times 10 to the 1st, and 8 times 10 to the 0. Does it have any powers that seem to be missing? It doesn't. That's actually really good news, because what that means is all I have to do is to write down the numbers that are being multiplied by the powers of 10 in order, and I'll have the value I'm looking at. So I have a 5, a 0, a 3, a 5, a 6, and an 8. We can go back in and put a comma in the right place, and we're just reading off that first value that's being multiplied by the powers of 10. Okay, so far so good? You know this. There's nothing about this that's like new information. You may not have seen it expressed quite like this before, but this is what these values mean according to the placeholder where they are. Now, this is going to feel like a little bit of an aside, like why did we just do that? But I promise we'll get to the why in just a second. There's a property called the distributive property that you've seen before. Usually the property is seen from the right-hand side of this that moved to the left. Right? So you usually see this piece expressed, and then somebody does some arching arrows like this or whatever, and you distribute in this case, the A through to the other two pieces that have the addition between them. That's usually how it's expressed. Because it's an equation, it can be written in either order though. And there actually is a really good reason why it's being written with B times A plus C times A, based on what we're about to do with it. Okay? This is distributive property. It just says that if I have two numbers that are added and I have another number being multiplied, then I can actually multiply that through the parentheses. And you saw this used considerably in algebra, right? When you were doing things like foiling or distributing out things with polynomials, right? All those words that we're not working with here. But that's where you see it used a lot in high school, okay? So we have all of our real numbers, A, B, and C, that this works for. And so let's take a look at what it is that is going to use this. Okay, so the directions here say to add or subtract in expanded form. Now what you'll notice is the problem is not given to you in expanded form. 75 plus 34. Number one, you got a calculator. Can you add this together in your calculator? Sure. Number two, this is simple arithmetic, like second grade maximum stuff where you learn this stuff. So you can do this by hand. The problem is that there's going to be a place inside of MyMathLab that's going to expect to see all the pieces written out in expanded form. So that's what I need to show you on what they're expecting. Now, we looked at what expanded form looks like on the previous slides. We said that 75 is understood as 7 times 10 and 5 times 1, right? We also said that we could rewrite this as 10 to the 1 for 10 and 10 to the 0 for 5, by the 5 rather. And we can do the same thing with the 34. So I can write 3 times 10 or 10 to the 1. And I can write the 4 times 10 to the 0. So I'm going to show this to you in sort of left to right form so you can see the distributive property in play. And then I'm going to show this to you in a vertical form that looks a little bit more like MyMathLab has you actually put the data in. Okay? So what this is actually saying from the distributive property is that the ones that are being multiplied by the same thing, like 10 to the 1, you could group them together. And instead of actually multiplying each of those by 10 to the 1, you could add the 7 and the 3 together first and then multiply it by 10 to the 1. Okay? Now, if you think about it, that's what you would do if somebody handed you 7 $10 bills and 5 ones, and then 3 $10 bills and 4 ones, right? You'd group all your 10s together and you'd group all your 1s together and you'd sort of count each of the individual groups. And this is what we do. And you can do the same thing with the 10 to the zeros. So we have 5 plus 4, and it's 10 to the 0. Okay, so if we do that, we have 10 times 10 to the 1, and we have 9 times 10 to the 0. Parentheses are necessary on at least one of the two factors. They aren't really necessary on both like I've done at the first piece. And then what happens when I have 10 times 10? Think about what happens if you have 10 $10 bills. It's equal to a $100 bill, right? So it can be traded up, if you wanted as few bills as possible, into a $100 bill. So it's really 100. There'd be 0 10s left over, and there'd be 9 1s. Or we could write this as 10 squared, 10 to the first, and 10 to the 0. Okay, so that's what the distributive property is doing in sort of a long view, if you're thinking about it from left to right. The way that my math lab has you write it in is actually a little bit more compacted, but the distributive property is a little bit hidden. And so it looks like this instead. You have your 7 times the 10 to the 1, and you have your 5 times 10 to the 0. Notice I'm using dots instead of parentheses. I think my math lab uses dots. It doesn't really matter. And then underneath it, I'm going to have the other one. So it's the 3 times 10 to the 1 and the 4 times 10 to the 0. I line up the ones that are in the same place value. Right, so it's the same thing as pushing them together, like in my second line over here where I moved them together. That's what this vertical format looks like. And I add from right to left, so there, or you can actually even add from left to right, doesn't matter. But there's 9 10 to the zeros, and there's 10 10 to the 1s, like this. And then the 10 10 to the 1s actually is equal to 10 squared. None left over. No 10s left over, and then we have our 9 times 10 to the 0. So it kind of makes it look like you have, like in my side of my math lab, it puts these little boxes everywhere, and you just fill in numbers, right? So it's going to have all these boxes in these places and so forth, and you're going to fill them in according to your data. Does that make sense? Okay, so that's what it's going to look like. Let's do one with subtraction, and we'll just jump to this version of it because this is what it looks like in my math lab, and understand that in the setup itself is the distributive property at play, sort of behind the scenes. So if we have 74, we would write that as 7 times 10 to the 1 and 4 times 10 to the 0, dots or parentheses, either way. That's a good question. So these two pieces are added, okay? So if I have 74, I have 7 10s and I have 4 1s. There is a subtraction coming up. It's down here, though. So I'm going to subtract off 4 times 10 to the 1 and the 8 times 10 to the 0. And the reason the subtraction is going in both places is because I'm supposed to be subtracting off the 40 and I'm subtracting off the 8 that's there. So you see the 8 showing up in both places. Now there's a problem. As this is written, though, what problem do you see? Yeah, there's a 4 in the top number, there's an 8 in the bottom number, and like legit, we don't have enough to take it away, right? There's not enough in the first number, the top number, to take away the bottom number. So what we do is we borrow, and the way that looks is that we actually take a moment. Let me see how I wrote it. To regroup. So we take one of these away. So imagine taking a $10 bill and turning it into how many ones? 10 ones, right? A $10 bill is worth 10 ones. So we take our 10 ones and we add them to our 4 ones and we have 14 ones. Okay, so when we do, we pay our kids for their chores, some of their chores. Some of them they have to do for nothing, but some of them they get paid for. We do this kind of thing every week. Every 2 weeks, actually. And I'll turn that $5 bill that I gave them into 5 ones so that they can break it apart and they can put some of it in giving and some of it in the church and some of it in saving, and right? We do this all the time. We break something apart into smaller bills. That's what's happening here. So in a very real sense, the second thing that'll show up inside of my math lab is another line here that says, well, what does it look like if you regroup and you put these numbers in like this? And you have your minus your 4 times 10 to the 1 and minus your 8 times 10 to the 0, and you would subtract. Again, you can go from left to right or right to left. There's 6 minus 4 is 2. And then you have 14 minus 8, which would be 6. And at the end of all of this, my math lab also has you write the answer generally. So it will say that this is 26. And the first one was 109. So what we're really doing is we're really getting a better understanding of how we sort of regroup things in base 10 when we do the subtraction or when we do the addition if there's any regrouping needed. All right. Have you heard of an abacus? Yes. Okay. Most of you probably have. Old school calculator. That's the idea. Okay. So predates our calculators. It's one of the oldest methods for speed calculating. This down here is the most common version of an abacus, at least a picture representation of one, right? Not the actual physical object, okay? And you'll notice some features about it. So the first thing is that the beads that are toward the middle, the ones that they've sort of darkened into this black color, those beads are active. They're actively part of the number we're working with. The blue beads that are sort of pushed away from the middle are inactive. Like remember, this is an actual physical object. You don't actually take the beads off the rods. They're there, they're stuck there, right? It's all glued together. So if you wanted to be able to say that the bead was being used, you need a place for it to be used and you need a place for it to not be used. So push toward the middle, it's being used. Pushed away, it's not being used. The beads above the rod are worth 5 and the beads below the rod are worth 1. Why? Well, because we could use fewer beads to get the same numbers, and that's actually very helpful. If you want to think about when you're making these, right, or even just now, right, like if it costs you less money to make the object, that's a good thing. So this is a way for the object to be made with fewer beads. That's a good thing. And the base 10 place values are listed, the smallest values on the right, just like our place value system, and they get bigger as we go to the left. Right, so this is the ones place, and then you've got the tens place, and then the hundreds place, and so on as you move from right to left. So let's take a moment and just identify what beads here we have, what this number is that it's being represented. So if you take a look on this one, all of these beads here in the middle, I'm going to circle them in yellow, are the active beads. On the first one, just we'll go from the left to right, the bead at the top is not active, but there's 3 beads at the bottom. The beads at the bottom are worth 1, so what number is represented on the first rung? It's a 3. So this row is a 3. The second row, again, the blue bead at the top is not active. The 1 bead right here is. So this one is the number 1. Finally, on the third rod that we have, the one on top is actually active. Okay, and it's worth 5, right, Cabrana? Yeah, it's 5. And then I've got 2 more down here. So what's the total of these beads? It's 7. This is how this number 7 would be represented. What happens if there's no beads in the middle? That's a 0. And then on our last one, we have 1 bead above and 1 bead below. It's the number 6. So this would be how we would represent the number 31,706. Okay? All right. So let's take a look at one that I want you to actually take a look at. Write it down, what you think the number is that this represents. Once you've written it down, you're pretty sure, turn to a neighbor and see if you agree. And then we will reconvene and make sure that everybody has the same answer, okay? So what number do you believe that this is? Not out loud, on paper. Share with somebody nearby. See if you get the same thing. Connect with somebody before you, in front of you, behind you, beside you. I don't care. Somebody. Connect with somebody. You got it wrong. Okay. Okay. Does everybody have an answer written down? Mostly in agreement? Okay, what is our number represented on number 5?
10,256.
Okay, and that sounded pretty in unison, so I think we've done well. 10,256. Is that okay? Yes? Now's the time to ask if that's not okay. Okay, do you have a question, RJ?
Why is it 56 at the end?
Okay, so why is it 56 at the end? Somebody help us out.
Because the numbers that are out on
Okay, the number above the rod's a 5, so this one's 5, so there's the 50. This one's also 5 with one below for a 6. Okay. Okay, we're going to go in reverse. We're going to actually draw a picture now of one of these, okay? So here's the deal. As you draw this in your notes, you need to draw all the beads in place, obviously, right? Because these are physical objects. You can't take off the beads. I believe this is multiple choice in my math lab, which means you're just going to choose which one matches the right number that they give you. I think that's how they do it because I don't think they have a sliding beads. That'd be a pretty cool feature that we should request that. So we're going to draw it the way we would if we were drawing it on paper. So we're going to draw our line in the middle, our rod at the top, our rod at the bottom. Bottom one needs to be a little further away because we've got more to draw within there. And then our edges. There are 5 rods on this abacus, okay? All right. And as we draw our beads need to actually be all there. So no missing beads allowed. I'll draw mine. We'll try and draw them in yellow just so that they distinguish on the background from the white that I've drawn with my rods. All right, so 70,000. If you're thinking about the numbers, the beads that are pushed to the middle line, what is it going to be that's pushed to the middle line? 1 on top, 2 on bottom. My beads are not going to be perfect, so just forgive me, but try to make them a little bit better. That's all right. Okay, but there's missing beads. Every rod needs to have 1 bead on top. We've got that one. It needs to have 4 beads on bottom. I only have 2. So what do I do for my other 2 beads? I push them to the bottom of the screen, right? And so I think let's do this. Hang on, let me move this up just so I have a little bit more space to work with. Oh my goodness, that's not what I want to do at all. Yeah, no, this isn't working. Let me do this. All right. My picture was just not long enough. Okay, 1 more in the middle, and then I've got the 2 at the bottom. There we go. They're oblong and funky. Why are there 2 at the bottom? Every rod has 5 beads on it. 1 above the line and 4 below the line. Okay, so we have to have them either pushed to the middle if they're active or pushed away if they're inactive, but there still have to be beads there. Okay, the next number is a 0. What do I do to get 0? Yep, 1 at the very top and 4 at the very bottom. So nothing is pushed to the middle on this one, right? So 1 there, and they've got 1 here, 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 and here, and they're not drawn perfectly, but I think we have the right idea. What about the number 1? Okay, 1 from the bottom is pushed to the middle. There's 3 pushed away on the bottom. And then there's 1 pushed away on top. Good job. How do I get 6? All right, 1 from the top and 1 from the bottom. So I've already got the 1 bead on top there. What else do I need? 3 beads on bottom. 1, 2, 3, kind of. And then 3. How do I get the number 3? 3 active beads on bottom, push toward the middle. What else do I need? 1 at the very top, 1 at the very bottom. Okay, what do you think? Is it okay? All right, cool. So abacus, this is how we would be representing these numbers on here. There's one more thing in this section that we're going to take a look at. And this is called the lattice method for products. So my elementary education folks, we do this also in number theory. So you may have seen that for those of you who've had that class. And to be perfectly honest, some of you have probably seen this in school. Okay, you may or may not, but you may. So these are in curriculums that are widely used in elementary schools today. And they came into play about when you guys were there. So I will tell you, so my daughter, who's a junior in college, so she's a little bit older than some of you, but awfully close, right? Like we're close in age, right? When she first learned how to do multiplication, like standard multiplication, she really struggled. And she doesn't struggle with math. Like this was sort of an abnormal thing for her. And so because I teach classes, for people who are going to teach kids her age, she and I went through several different other, we call them algorithms, ways of doing long multiplication, right? And this is the one, for whatever reason, that made sense to her. So it's a very clever way of doing this. It's called lattice method for products. You create rows and columns for your digits. You divide each box along the diagonals. You compute each single digit product according to the tens digit in the top left, recording tens digit on top left, ones digit on bottom right, and you add along the diagonals. This is the step-by-step process, okay? It's a little cumbersome to write down, okay? So when we draw it out, you're going to be like, ugh. Okay, that's good. But you know what the standard algorithm is too? It's kind of cumbersome to write down, kind of detailed, right? But once again, let me point out to you the fact that when we do these problems, you should be checking your work with calculator. There's no reason not to, right? You can check and make sure that you didn't accidentally write down that 9 times 7 was 56 instead of 72 or 47 or whatever number. You can check to make sure that you didn't accidentally remember a multiplication fact wrong. You can do that, right? Or that your addition actually adds up, or that the answer actually is the right answer. So while this process is not meant to be done in that way, there's nothing wrong with checking your work as you do it, okay? So I'll do an example on this slide, and then we will do another one on the next slide. So we're still writing. So I'm going to do the example 23 times 187. All right, so you're going to draw a box. And your box needs to be either 3 wide and 2 long or 2 wide and 3 long. It does not matter. I'm going to make my box 3 wide and 2 long because my space fits a little bit better for that. So I have a 3 by 2 grid. Okay, so on the outside of that grid, on the top and on the right, we're going to put the numbers that we're multiplying. So I'm multiplying 187, which I'm going to put on the top because I made mine 3 wide, and 23, which I will put on the right because I made it 2 long. Okay, is that okay? All right. It talked about dividing each of these boxes along the diagonal. So that's what this is doing. We're splitting our boxes into diagonal halves. Okay, pretty good so far. All right. So this is not a very exciting box in the top left-hand corner to start with, but we're just going to work from left to right, okay? What is 1 times 2? It's 2, right? So you're going to multiply the column that you're on by the row that you're on. So 1 times 2 is 2. The ones digit goes in the bottom right. A tens digit will go in the top left. We'll see that happen on the next one. So the next one, I'm in the row 8. Column 8 and row 2. So 8 times 2 is 16. So I write the 1 here and the 6 here. The next one is in the 7s column in the 2. So 7 times 2 is 14. 1 on the top, 4 on the bottom. And we go to the next row. 1 times 3 is 3. So it's bottom right. 8 times 3 is 24. So a 2 here and a 4 here. And then the 7 times the 3 is 21. Okay, so why in the world is this method any maybe better or different even than the other method? Well, here's the thing. If you do the standard algorithm for multiplication, in the middle of doing multiplication, you do addition. Let me show you what I mean if you're not following on that for a second. We would write down 187 times 23, and we would say 7 times 3 is 21. We write down the 1, and we carry the 2. And then we'd say 3 times 8 is 24. And in the middle of doing a multiplication problem, what do I do with the 2? You add it. Do you have a sense of how that could be a little confusing? It could be, and it was. So in the example of my daughter, and again, she's not a weak math student. She's a strong math student, and still just doing that operation in that order in the middle of the problem did not work well for her. at the time. So this method was not going to do that well for her, and the other one does. And so we would continue, and we would say that we've got, 26, and we would carry the 2, and we do the same thing. 3 times 1 is 3, plus 2 is 6, and then there's this mysterious 0 that shows up from nowhere. It doesn't really show up from nowhere, but it kind of looks like it, right? You throw this 0 in. It's thrown in there because I'm not really multiplying by 2, I'm multiplying by 20. And the 0 is in the ones place in the number 20. So there's a 0 there. Okay, so I'm going to pause. I'm not going to finish the problem from this perspective. Let's come back over to our lattice and see how it finishes then, okay? So we find all the multiplication in all the little boxes. And that's what you're going to do inside of my math lab. They're going to draw you a grid, and you're going to fill in all the little boxes, right? And you can do that. It's not a problem. What you're going to do then is you're going to extend the diagonals for each of the diagonals that are present there. So I'm just going to draw them longer. Like that, just extend them down. And we're going to start in the bottom right-hand corner. And what we're going to do is we're going to look inside of the boxes. So we're not looking at the 1, 8, 7, 2, and 3. Those are not up for discussion right now, okay? It's only the numbers in the boxes. And anything that's in the box on that diagonal we add together. This bottom one's not very exciting. It's the number 1, right? But the next one's a little bit better. I have 4 plus 2 plus 4. What is that? That's 10. So I write the 0 and I carry the 1. So I didn't, and that is a 1 that's carried. Maybe I'll do it in yellow just so that I distinguish it from the one that's already there. I do end up carrying, just like I carried over here, but I don't do it in the middle of multiplying. I still do it when I'm doing addition. And that part separates those operations out kind of nicely. So now I have 1 plus 1 is, plus 6 is, 8 plus 2 is, 10 plus 3 is 13. So I have a 3 down here in the bottom. And I carry my 1. And then I have 1 plus 1 plus 2 is 4. And then the answer to the problem is right here. It's 4,301. And how could you check it? With your calculator, right? You grab your calculator and you go 187 times 23, or in reverse, and it will tell you 4,301. Okay, so let's try one more together. A little bit bigger. This one is 912 times 483. Okay, so how big is my box going to be? A 3 by 3 box, you got it. So I need 3 rows, 3 columns, and it doesn't matter whether I put the numbers on the top or on the right because it is a 3 by 3. It's symmetric. So I'm just going to go in order. I have 9, 1, 2, and 4, 8, 3. What's my next step? Okay, first I need to split the boxes, right? Okay, so we're going to split all of our boxes apart. Just like that. And then what we're going to do? Yeah, we're going to multiply within the boxes. So first row, and I'm just going to go across. So column 1, row 1. 9 times 4 is 36. 1 times 4 is 4. 2 times 4 is 8. Everybody good with that row? Okay, row number 2. 9 times 8 is 72. 1 times 8 is, and 2 times 8 is 16. Y'all are doing good. 9 times 3, 27. 1 times 3, 2 times 3, 6. Now what? Okay, we're going to add. We're going to extend our diagonals and add. So let's extend the diagonals first. Okay, it does matter that we start with the diagonals in the right place, right? We have to start in the bottom right-hand corner. That's my 6. So here's a 6 down here. Next row, or next diagonal is 6 plus 3, which is 9. And then I have 8 plus 1 is 9, plus another 8 is 17, plus 7 is 24. In some order anyway. However, whatever order you'd like to do. It's 24, yeah. So we're going to put the 4 down, and we're going to carry a 2. Notice I changed colors to try to help us out. Okay. I have 2 plus 4 plus 2 plus 2. 10. Good. Carry my 1. 1 plus 6 plus 7. 14. Carry my 1 one more time for a 4. The answer is out here. It's a long one. I have 440,496. 440,496. Somebody check the calculator just to make sure we didn't make any mistakes real quick for me.
Yep, that's right.
That's right. Awesome. Okay, y'all good? Okay.